All right, cool kids. Who has something they think will fill in one of these? Ready, set, go. Elimination, I like it. I'm putting it second. Because it was section 7.2. Substitution, I'm putting it first because it was section 7.1. I like it, and it was involved kind of in all of them. So it's not like its own blank, but it was good, Robbie. It was in there. Row echelon, I like it. Is row echelon technically an application of elimination? Yes. But I'm still going to put it. We're going to learn something new this chapter called reduced row echelon. Partial fractions were a part of applying systems of equations. Like it's an application. Same thing with the constraints and all that jazz. Inequalities, well, technically we say equations, so I guess it wouldn't be under this category. Substitution, elimination, row echelon. Interesting. We haven't reviewed it, but it is review now from Algebra 2. Matrices. We haven't covered it, but you did in Algebra 2. Matrices. And this is the reason, yeah, literally. Actually, they could probably help you remember because they are a little bit ahead of us as far as matrices. Matrices, a rectangular array of real numbers. If you guys have your calculators out today, I'm not going to totally teach you how to use it today. I'm not going to totally teach you how to use it today, but let's just make sure we can at least find them in our calculators. Guys, is there a place to go for matrices in your calculators? Yeah, where? Yeah, it is called matrix. Show someone in your group how to get there. Now, there's a lot of stuff under matrix. Make sure everyone knows the button, knows the option. Some people don't have their calculators. Make sure Jason and Johan see it. Has anybody gone to edit yet? The matrix menu and then edit? Hit enter on edit because then you can put in a matrix. I want you guys to play with the numbers. There's something at the very top that has like a little X, like a multiplication sign, but it doesn't multiply. If I were to tell you guys about a piece of wood, go down to Home Depot and I want you to buy a 2x4, does that mean 2 times 4, so go get an 8? No. Why do I call it a 2x4? 2 feet by 4 feet. I know, struggle. Or 2 inches by 4, yeah, but like if you're talking about a 2x4. So it could be 2 units by 4 units if it was something else. What's going on in your calculator as soon as you hit matrix and edit? What if you put in a 2x4? Do you see it? Gavin, is it there? 2x4. What kind of size rectangular array of numbers does the calculator, the computing agent, now give you? How 2x4 to me? And don't just say 2x4. Okay, so according to Kyle, there are 2 columns. And each column has how many elements? Is that what it looks like? That's what Kyle says, but he doesn't have his calculator. So you guys have to help him out. Is it 2 columns by 4 rows, or is it 2 rows by 4 columns? Ooh. All right, so it's not that one. So we need to write something to remind us that it's rows first and then columns second. Hey, that's what's coming. Entries. So it would be 1, 2 rows. You guys remember what rows and columns are now? Okay, 2 rows and 4 columns. 2 rows and 4 columns. Let's come talk about stuff. Matrices are a rectangular array of real numbers. Order. We could say the order is m by n. That's what we were just saying about what your calculator is asking as far as what size to make the matrix. The order of it is, in this example, 2 by 4 would be the order, but the first number stands for how many rows, and the second number stands for how many columns. The entries are the actual little guys that go inside each of the boxes. So the entries, I'm going to say A, and this A shows up again when we talk about sequences and series, but that's not for a couple chapters still. But A sub 1, A sub 2, A sub 3, that's a notation for in the future we're going to talk about. But in this one, we can't just say A sub 1 or A sub 2 because we have rows and columns. So we're going to have to do two subscripts, M and N. We're going to have to do M and N. So up here, now I know some of you guys, this might be a little too small for you, so let me make it a little bit bigger now that we know what size this is. If you want to write down an example, it might not be a bad idea. So we have two rows with 4 entries each. AKA 8 entries total, right? Are we good? Okay. But if I was to show you not the entries by numbers, like 1, 3, -4, 7, like if I was not to fill in with numbers, but instead fill in with notation about which entry I was referring to, this would be A sub 1, 1. This would be A sub 1, 2, A sub 1, 3, A sub 1, 4. What do those stand for? Oh, A11, A12, A13. No, 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 no. A1, 1, 1, 2, 1, 3, 1, 4. Because all of these are in the first row, row 1. But what column are they in? Column 1, column 2, column 3, column 4. You guys ever played Battleship? Yes. Have you ever had to talk about the different placements of where you're trying to throw and lob your bombs? Do you have to deal with rows and columns? But what made that easier? Weren't the rows, ooh, help me out. Are the rows letters and the columns numbers? It's been a long time. Letters and then numbers? Cool. So you go E and then 5. What's the problem with matrices? It's 1 and then 1. What? But we always know the rows number comes first and the columns number comes second. So it'd be nice if it was letters, but let's be honest, we're in math. The letters stand for numbers. So instead of doing like a battleship thing, which is easier for the common brain, we're going to have to actually deal with two numbers, 1, 1, 1, 2, 1, 3, 1, 4. So guys, what would this entry be? 2, 3. Does that make sense? What would this entry be? A2, 1. This one? A2, 4. And this one? Are we good? Because we're dealing with the row number and the column numbers. Is that cool? So if you need to write that down, totally cool. What would change if I had a 3 by 4? Well, now all of a sudden I'd have A31, A32, A33, A34, etc., etc., etc. How big can matrices be? However big you want them. But what's cool? What's cool? Do you want me just to kind of show you a peek behind the curtain right now? Okay. What if I was to give you something? Let's just do it up here on the screen. You guys have your graphing calculators out, right? But remember, in this class, are we just trying to figure out how to use that little baby instrument to make us feel smart? No. Someday I want some of you designing stuff like that to make everybody else's lives better who don't have the time or the energy or the skills to program, but they do need the instruments. I want you to understand why or how it does what it does. Maybe not with the computer programming. Hey, take AP Computer Principles next year. But at least the logic that is necessary to tell it what to do. I want you guys to do the following. Ready? You don't need to actually write it in your notes, but be ready in your matrix menu with edit. Don't have made the size of the matrix yet. What if I was to give you something like 3x plus 2y minus, actually let's not even do that. Let's do it this way. Let's do 3a plus 4b minus 5c plus 6d minus 7. I'm going to go F because E stands for something in math. And then let's go ahead and do 2a minus 3b plus c. And let's just say there's no d, and let's just do like minus 3f. We'll say that one equals 1. We'll say this one equals 10. Let's do a plus b minus 4c minus 5d. Let's say there's no f in that one, equals 17. Let's say 1/2a minus b plus 172c minus 36d plus 1/5 f is equal to negative 20. Wait a minute, why am I making so many equations? Because I have so many unknowns. And for however many 1, 2, 3, 4, 5 unknowns I have, how many equations do I need? Oh, so I still need one more? Let's not have any a's, and then let's go ahead and have 14b minus 21c C plus 34D minus F equals 0. Could our row echelon form by hand tackle this problem if you had a huge piece of paper? How? What do you think we would do? Row 1, row 2, eliminate who? A. Row 2, row 3, eliminate who? A. Row 3, row 4, eliminate who? A. Row 4, row 5, eliminate who? A. Now we have all sorts of equations. Technically we'd have 1, 2, 3, and 4. We'd have 4 equations with all the A's gone. What would we go for next? Eliminate B, eliminate B, eliminate B. We'd have 3 equations left. What would we eliminate? C, eliminate C. We'd have 2 equations left with 2 unknowns, D and F. Can we get D and F with 2 equations, 2 unknowns? Substitution, elimination, whatever you want. Yeah. As soon as we have D and F, what are we going to do? Go plug them in and get numbers and move them all to the other side. What are we going to have left? Just A's, B's, and C's. Sweet. A's, B's, and C's, that's old school. We can just go ahead and take 2 and take 2, eliminate the A's, and then take 2, eliminate the B's, and we have our C, go back to B, go back to A. Whew! That took me like 60 seconds to say, but how much time would it take it to do? But is there a systematic approach to the problem? What do I want you guys to do right now? I want you to put all these numbers in a matrix. Whoa. What size do we need? How many rows? 5. How many columns? 5. Oh, 6. Spoiling the fun. Somebody in your group, at least one. Some of you don't have calculators. That's okay. Throw the whole thing in the calculator. In our heads, we have a systematic approach that we could all get to the answer the exact same way, and if we don't agree when we get there, we could check each of our steps because we should have done it the same way. I'm glad. Thanks, bud. Oh, no, but some of them don't have spaces for... Oh, we put zeros. Oh, okay. That makes sense. That makes sense. Now, to be honest, kiddos, I totally made up all of this, the whole thing. I mean, I knew it had to be 5 equations, 5 unknowns. But where did those numbers come from? On the very last line, I was like, oh, I could have totally been choosing numbers that like came from my life. But I was like, nah, it's all right. Yep, I just wanted to have fun and have a big number. Same reason I put in a 1/5 and a 1/2. Anyway, and zeros in random places. Do I know if this has an answer? I don't know. What do I mean? It might be possible that all of these don't intersect. Wait a minute. This isn't 3rd dimension anymore. This is 5th dimension. What's the 5th dimension? 4th dimension, some people say is time. There's multiple dimensions? Oh, try Googling string theory. Have fun with that one. Anyway, coming back. Parallel universes? What? I don't know. Anyway, shh. Too much fun. Too much fun. Maybe there's not a great graphical way of talking about this, but in some way, shape, or form, out in the 5th dimension somewhere, could all of these intersect? Yeah, I suppose. We're going to have our calculators tell us how, but someone had to program the calculator to systematically approach whatever you could possibly give it of whatever size. Can your calculator deal with a 5 by 6? Yeah. Are you guys putting in numbers? Hopefully. But here's the question. How do we get it to do what we want? After you have all the numbers in, has anybody seen when you hit that matrix button the first time, before you hit enter on edit, that there's something called math? Do you remember when you hit the math button on your calculator, aren't there all sorts of cool things that your calculator can do? If you're in the matrix menu and you hit the math button, there are all sorts of cool things your calculator can do. Now you want to be on your home screen. You don't want to be inside editing a matrix. You want to, once this is in, it's probably called A. Is it matrix A for all of you guys? Is that what you're editing? Okay. You want to exit out of the matrix menu, go to the home screen, get out of the editing, and then you want to go to your matrix menu and hit that math button. Didn't we say one way of solving was something called row echelon form, and I hinted it had something to do with programming your calculator? Is there an REF, row echelon form? Is there an REF feature of your calculator? Ooh, can you hit REF and enter? Oh no, it shows a parenthesis. If you hit enter on the home screen, it won't do anything. Why? Well, you have to go tell it which matrix to REF to get into REF. So go back to matrix. Is there something called name? Pull Robbie up. And then put A. All right, Adam, catch Jason up. I am curious what your calculator is giving you. You're trying to do REF, row echelon form. Do they put the matrices in brackets or something? Is that true? Adam, did it do it? Did it do it, Sam? Oh, do some of you have nasty decimals in there? Oh, it'd be sure nice if they could put... Ooh, hey, math button. Is there a go to fractions in the math menu? Hit the go to fractions button. Ooh, does it get prettier all of a sudden? Is it nicer now? Well, remember, Aiden, my numbers were a little random. Does anybody have the nice fractions? Oh, no? The ones that are able to go into fractions. Okay, what do we got?
Wait, did I have to put in X's or only the numbers?
Only the numbers. So wait, are you guys seeing 1 and then 4 thirds and then negative 5 thirds and then 2 and then negative 7 thirds? Can I borrow someone else's calculator? Gracias. The first row was good? Okay, and then 0? 0? No, 1, right? And then negative 3 halves, and then 17 sevenths. If someone's tracking with me, Aiden's poor calculator. Negative 1/14. And then, is it 0, 0, 1? And then negative, this is the number that they were getting a kick out of, 692 all over 3,577. Oh no, they didn't give me a nice fraction. Why? Because there's not really a nice fraction to go along with it. We'll just put dot to dot. And then we have, wait a minute. What does row echelon form give us? Do you guys remember? What's so nice about row echelon form? Robbie, it's your turn. What's so nice about row echelon form? What was that answer you were trying to answer and I said no? Back substitute. Why is row echelon form so great? Well, hold on. Wait. When we put this into our matrices in our calculator, doesn't row 1 really stand for equation 1? And doesn't row 2 stand for equation 2, equation 3, equation 4? What does column 1 stand for, though? A variables, B variables, C variables, D variable. Did I leave something off? Did I not keep scrolling? Oh. What did I miss? Is that right, but I missed the other side? Ah, thanks. Does anybody have that last portion you can read off to me real quickly?
It's 1/3.
1/3 is the first one? Okay.
0.
Okay.
Negative 11 over 92.
Okay.
Negative 1.6901. And then the last one is negative.
Oh, yeah. I wasn't scrolling enough. Okay, and the last one was what?
Negative 2.096.
How did I know something was wrong? Because where was my poor little F guy? And then equaling constants? Okay. So we're done, right? Well, we're not done. Who do we know? F equals. Do we know F? Yeah, because it's 1 F equals. But problem, what would we have to do in order to get D? Wouldn't we have to go back substitute to find D? Then wouldn't we have to go ahead and back substitute to find C? And then wouldn't we have to back substitute to find, you guys see what I'm doing? To find B? Then wouldn't we have to back substitute to find A? Now hold on. Do you think the calculator, if it was smart enough to get here, do you think it could get me all the way? Can you guys go do the exact same thing but with something called REF? Reduced row echelon form? Reduced row echelon form? Oh, it probably just has all the nasty decimals. Oh, don't use the alpha. Use the name. I know it's annoying, but you go like that. There we go. And then it can. It's just going to write it funky. Yeah. Your numbers are a little weird, but you might have put it in just a little off. Oh, yeah. Okay, it probably just went a little off. What you can do in the fractions, instead of 0.5, you should be able to do that. And it'll do that for you, so you don't have to worry about it. Does that make sense? It just won't look pretty, but yeah, that works. What'd you guys see when you did REF? Wait, why is it nice, do you think, if you got 1, 2, 3, 4, 5? Oops. Why is this nice? What's the only thing in equation 1 now? 1a equals, ooh, what's it tell you? Yeah, let's do 2 decimals. 1b equals 1c equals 1d equals and 1f equals. What would have happened if you had done all this work? And how big can your matrix go? As big as you need. As many variables as you need. As many equations as you need. But did God create the TI graphing calculator with the matrix program and just put it in our laps and say, here you go? No. Creative human minds made the program to use the machine to do a lot of math in a very short amount of time. Cool. If you guys haven't watched the movie Hidden Figures, you should start watching it. It's a great movie. It just gives you just a peek at how much our lives changed once computers became accessible to companies, industries, families, down to individuals. But it took time. It took time. Because they used to be huge. And those huge computers, if you want to look at Hidden Figures, talking about the NASA space program, and when IBM was first brought in, it's just a cool, not that I'm saying it's completely factual, but there were a lot of experts and a lot of eyewitnesses, etc., that were included. Not that it's perfectly factual, once again, but the idea of, oh my goodness, this machine, and what were the calculations it was doing? If you watch the movie, listen carefully. Things like trig values and exponential values, addition, subtraction, multiplication, division, and it was earth-shattering for the calculations they needed to do. Well, atmosphere-shattering, I guess. Okay, hold on. So what am I trying to tell you about? Just a little peek at what we're doing this chapter. But where does it start? The basics. The basics. Matrices, super powerful things. Super powerful things. Now hold on. In chapter 7, didn't we realize in real life applications you actually have to figure out what your constraints are? Okay, it was nice and easy. They told you in a paragraph, guess what? This has to be true. If you actually had your own company, though, wouldn't you have to have, like, I don't know, economists and financial advisors, etc., to figure out all of these constraints for you? What's practical, what's necessary, what's possible, what's financially plausible? Anyway, so in real life, trying to figure out your constraints, trying to figure out all these different equations that need to be true and what all the different variables are, way more complicated. But matrices can deal with a lot of information. And if you can figure out how to have systematic approaches to dealing with the matrices, well, maybe you have a peek at the programming as well. But the basics. Well, hold on. The basics. How do we know what order this would be? If you wanted to get this in your calculator, what would you make the order? What by what? Oh, it's a 1 by 1. That's easy. How about this one? 1 by 4. 1 row, 4 columns. How about this one? 2 by 2. How about this one? 3 by 2. Okay. I want to make sure that you know how to describe the size of a matrix. Basics, basics. When we come over here, the special matrices, let me scroll down just a little bit. Does it make sense that if a matrix is a 1 by anything, it would be called a row matrix? Because it literally just has one row, right? So any row matrix, just literally one row. It'll be a 1 by n. It could be a 1 by 5, a 1 by 10, a 1 by 20. But a 1 by anything just has one row. But an anything by 1 will just have one column. True? Square matrix. I'm calling it an n by n. Why? However many rows must match however many columns. Now, the one that we just put in was a 5 by 6. It wasn't a square matrix. But what about the variable component? Was that a square matrix? 5 variables? 5 equations? Now, we did a 5 by 6 because we had all the constants on the other side, but the variable portion was a square matrix. Gavin, I'm sorry, you had a question, kiddo. Just the size. Yeah, just the size. The order is the snazzy way of saying the size, the rows and columns. Kyle.
So last year when we were writing a Daniel matrix, now that we know system equations, I understand why there's all those zeros.
And why a goal of ours is going to be reduced row echelon form, getting the identity matrix. Yeah. If possible. Ooh. Are there equations that you could plug into? Remember I warned you? Are there equations you could plug into your graphing calculator? Ask for RREF and it doesn't get you to the identity matrix? If it doesn't get you to the identity matrix, that means there's not just one solution. So there could be infinitely many solutions. So we would have to check out and say, okay, hold on. What if this is missing? What if it's all zeros? Oh, something went away. I'm going to have to say like Z equals F equals D equals A. And then I can define the rest. So even though the calculator can do a lot of good things, it's still restricted, and it's not going to be able to tell you what Z equals A, and oh, by the way, there are infinite and many solutions, but we, analyzing the data, can take extra step. Square matrix with a main diagonal of 1s and the rest of the entries as zeros. If we can, in a system of equations, get the variable portion to be an identity matrix, we will have the identities of each of our variables. But the identity matrix is also special because it is the one matrix when multiplied by, when able to be multiplied by. If you guys remember anything from last year about matrix multiplication, sometimes it works and sometimes it doesn't, depending on the size of the matrices. Sometimes you can multiply and sometimes it's illegal. But the identity matrix is also the additive identity, 0. Any number plus 0 is itself. The multiplicative identity of just numbers is 1. Any number times 1 is itself. The identity matrix is the one matrix, depending on the size of the matrix we're multiplying by, where a matrix times it will be itself. Which is helpful for inverses, etc. Ooh, inverse matrices. That sounds complicated, but the cool thing is, matrix multiplication has so many different components to it that's actually a way of encoding messages, of encrypting information. And the only way to decipher, to decode these encoded matrices, encoded by matrix multiplication, is with an inverse matrix. Otherwise, the message would forever stay hidden. Maybe we should watch the Enigma code too. Anyway, the end of this chapter ends in cryptography. coded messages. And only showing you one way with matrix multiplication, but it'll be fun. It'll be fun. Although the movie wasn't called The Enigma, was it? What was it called? Benedict Cumberbatch. There was a bit of a political agenda in it, which is kind of sad. Not that it wasn't somewhat factual, but the political agenda was a little annoying at times. Was it the Enigma code? Yeah. Maybe it was just called that. I don't remember. Okay. And it was doing very similar math to the IBM machine at NASA with hidden figures. Well, that one's a bit bigger, I think. You guys see that there's just a special name for taking a system of equations and making it into a matrix? Special name, augmented matrix. Okay, whatever. It's taking a system of equations, and if there is any, we have to have X column, Y column, Z column. If we mess that up, we're giving the calculator bad information. Is there sometimes user error when it comes with technology? Yeah, there's sometimes user error. So that'd be a dilemma as far as needing to have it all nice and lined up for it to be able to process the information. But that's just called an augmented matrix. Row echelon form, Gaussian elimination, can be used, but if we do row echelon form, which you guys just saw is REF in the calculator of, I'm just going to put name, because you guys might not want to like delete a matrix A if you might have to use it again later, or something didn't work out, you want to check it in homework. You might need to make a matrix A, matrix B, matrix C. So REF of whatever we're going to do. But that's what we've already done, in that we got down to ones on the main diagonal, zeros everywhere below, but we were allowed to keep numbers up above because it's like, all right, we're going to do back substitution. And to be honest, REF only takes half the work, maybe 2/3 of the work of our REF. But what was the difference about what we were left with at the end of REF versus our REF? We still had a lot of work to do. Now, if we have smaller systems, there wouldn't be as much work to do. Maybe it wouldn't be a big deal. Maybe it's better to save work on this end and not have to keep going to RREF. Every now and then that might be true. But eventually we will want to get to RREF. Hold on. Wait. But we had a system. We had a system for REF last chapter. Wasn't it on your test? We had a system for REF last chapter. So how do we apply that system to the matrix? What was the very first part of the system for REF when we had just equations? No matrix. What was the first thing we did? Eliminate the x's using what two rows? R1 and R2. And then we eliminate the x's using R2 and R3. So let's see how that translates to matrices. Ready? We can actually do that over here, and we can say, you know what? We're going to take R1. Well, your honors. Do I want to go here? I think I will. Okay. Can I take A11 and A12? Sorry, A11 and A21? You guys know what I'm talking about as far as notation, right? Okay. I'm going to take A11 times R2. A11 times R2 minus 21. That's the math I'm going to do, the little baby equation, to get my next system, or my next matrix. What am I doing? Okay, I'm taking the -1. I'm multiplying it by the first row. Oh, I'm going backwards, sorry. I'm taking A11. I'm taking 1, multiplying it by the bottom row. And then I'm subtracting A21, -1, times the first row. And I'm putting it into R2. I'm keeping the first row, -4. 3, 5. I'm keeping him. But to get to my second row, to redo my second row, I'm going to say, all right, let's multiply him by him. So 1 times -1 is -1, right? Minus -1 times 1. Minus -1 is 0. Ooh, that's good. I want a 0, right? Okay. But how about, I don't know if it's going to work for this one, is it? We have to do, well, what we do to one thing, we have to do to the other, because remember equations, we have to keep it balanced. So we're going to do -4 times 3 is negative 12, right? Minus 3 times negative 4, minus negative 12. Oh. If we do 3 times negative 1, 3 times negative 1 is negative 3 minus negative 1 times 3. Wait, hold on. Everything's going to 0? Now pause. That's how you get zeros, is you multiply one by the other minus the other by 1. We could do elimination. We could always just say multiply them by themselves and make a sign opposite. But pause. Why is this not good for row echelon form? We're not wanting all zeros, are we? So pause. Did I say multiply every first entry by every second row? Or was it just him? Oh. What I was showing you was the idea of why multiply them by each other. But actually, we're only supposed to be using this number. Oh, just this number. So we multiplied R2 by 1, 1. And then row 1 by 2, negative 1. And we subtracted that 0. But we have to keep doing that for each one. So it's actually 1 times 3. We're not multiplying these by each other. 1 times 3 minus negative 1 times negative 4. Okay. Do you guys see how it might be nice if we could tell a computer to do that work for us, but it's going to be messy for us keeping track of all this mental math? So instead of doing that, even though we tell a computer to do that, because the computer doesn't know what numbers are being thrown at it, for our purposes, remember how I said we were creative? What happens if I just do R2 plus R1? What's 1 plus negative 1? 0. What's, well, I don't know, but I have to do it because I have to keep the operation. So I get negative 1, I would get 2, and I would get 2. Guess what we're going to do tomorrow? Keep playing with, well, how do we do REF ourselves so that we kind of understand the math? We'd make it a little more complicated for the computer, but how to program. Does that make sense? All right, cool kids. I'll see you later. Bye. That's the augmenting is saying, okay, this part of the matrix